Okay, I'm going to get started. There's a few things that I wanted to say about modular flow that I didn't get to mention yesterday. The simplest way to discuss modular flow is in the bipartite system, and in that case, you can already understand the essential features. So in that case, we take some operator acting on this Hilbert space, and we define this flowing operation like this. And so here, what I'm imagining is just I had some initial, say, bipartite pure state, and I get some density matrix, and I'm inverting it, so I need the density matrix to be invertible, but that's like the cyclic and separating condition. Okay, so one way to characterize this object is that it's a symmetry. So if I compute expectation values of this operator, O of S, then it's left invariant under this operation just because of cyclicity of the trace. Okay.
O is in A.
O is in A, yeah. Maybe I can label it. A, OA. So this follows from cyclicity. And then the next thing we do is we think about correlation functions. So rho A, OA. We have two operators. They're both in A. O1 and O2 are both acting on A. And let's think about this correlator a little bit. So let's write it out. So in particular, 1 plus IS, O1, rho A minus IS, O2. And if I think of S, so S, you should think of typically as a real parameter, but now I'm going to complexify S. So take S to be complex. And then, let me decompose S as T plus IY. And then we plug it into this equation, and we get rho A 1 minus Y this. And now if you remember the density matrices, I can diagonalize and like this, where the P's are probabilities, so they're less than 1. Then you can quite easily see if, let's say, my Hilbert space was infinite dimensional, then it's possible that these traces do not converge, right? Because I'm raising some number that's less than 1 to some power. If that power goes negative, then that trace can blow up. So in fact, the traces here, and if I insert complete sets of states here, will only converge in some window. In particular, I need this to be positive and this to be positive. These don't really matter because they just introduce phases. And so it converges as long as, so this, or in terms of the original S parameter, this is true. And so we can analytically continue this correlation function into the strip. So this is the complex strip. And so we draw some picture like this. This is the S plane. Here is the imaginary part of S. And it's, so it goes from 0 up to I here. And then we also notice the fact that if I take this correlation function and I set S to be equal to I, so let's say I started here and then I move up here. So when S is equal to I, what do you get? Well, you get a -1 here, so you just get O1 row A to the 1. So then I use cyclicity again to rearrange this, and I get trace row A, O2, O1. And so this is like the original correlator if I set S to 0, except I've switched the ordering of the operators. So the ordering switched. And this, this operation, or this equality, is called the KMS condition. And it characterizes this modular flow. Now, one way to say this is to let me erase this. One thing you can do is you can take this strip and just sort of replace it. Just make this function periodic in the complex plane. And then what you can think about is, well, now this point is the same as this point by periodicity. And so if I take the difference between these 2 points, that's the discontinuity across this branch cut. There's now a branch cut there. And you see that the discontinuity of this object across that branch cut is just the commutator. And so this should be quite familiar from quantum field theory and so forth, that you get a commutator like this. Good. And so I think it's, to understand this a little bit better, I think it's useful to go through a simple example. Again, the simplest example is just Rindler space. So Rindler space. And if I use coordinates, let's just do 2-dimensional Rindler space. And if I use these coordinates like this, then I can look at, okay, so now we're interested in correlation functions, and let's just say take a 2D CFT, in which case the 2-point functions, at least the primary operators, is fixed. And so I can write the answer down, and you know the answer. It's just, given the scaling dimension of these operators, it's just a function of the distance between these 2 points, which then I can write out in Rindler coordinates like this. Okay, so these R1 and R2 are, and eta 1 and eta 2 are just the locations of the 2 operator insertions. And so what is modular flow? Well, modular flow, now this correlates, so this is just the original correlator O1, O2. And now if I start flowing O1, then all I'm doing is I'm boosting the operator, which in these coordinates is just shifting this parameter. And then and so you can draw a picture of what's going on. Here's Rindler space, here's the Rindler wedge. And my A is over here, see? And I had some operator, say 2 is here, and 1 is here. Then I start boosting 1 by S, and it starts to boost. But at some point, it hits the light cone of the 2 operator, and you see a branch cut. So in particular, the analytic structure of this correlator 2 looks now like this. In fact, this is the same S strip that I was drawing before, except now there are branch points, and these branch points are exactly the light cone singularities. So here, it's when this operator it hits the light cone of operator 2, and then I can also trace it back, and it can also hit the past light cone of operator 2, and so these are these 2 branch points. So moving along here, and of course, when I hit a branch point, I can choose to go either way, and then the discontinuity in the different ways just gives you the 2 different orderings, and so that's what we found here via the KMS condition. Yes?
2 questions.
Yes?
in this version of the k-means condition, what happens to the arguments of the operators?
The arguments.
Both of them get continued.
Which arguments are you talking about? You mean the original locations of the operators? They're sort of implicit in the labeling. So if you like, this is O of x2, if this is a local operator, O of x1.
I have a question about the modular flow.
Yes.
Is there an information theoretic operation that corresponds to the flow?
Yeah, it is the flow. That is the information theoretic operation. You mean some kind of physical, yeah. I'm not sure. I don't know a good answer. Any other questions? Yeah.
I don't quite understand the k-means condition. So
yes.
So the trace of rho A O1 O2 is equal to the trace of rho A O2 O1 minus the commutator. Kind of obvious regardless of imposing any condition, right?
Well, no. The key. You know, no, but the key step is when I took this original correlator, and then I shifted it by I, and then I moved up here, and then I used periodicity, which is just a trick. It's a sleight of hand. So to put this back down here, and then the discontinuity.
But then you get a commutator.
Yeah.
You can state the k-means condition without.
Yeah, you don't have to do this. Yeah, I think it's. I like to think of it in terms of a commutator. But
Then it's like saying that the commutator boundary.
no, there's branch cuts. So you can only do this. You can only make this function periodic. But of course, there's going to be a discontinuity here. And in the local case, in the Rindler case, there's a gap here. So actually, there's a region where the two-point function is periodic. And the reason for that is that the operators are space-like separated, so they do commute. Okay. But in general, there's not going to be this gap.
It doesn't seem like a condition you're imposing, but just like something that happens. Right?
Sorry? What?
It doesn't look to me like it's a condition you're imposing somehow.
Oh, yeah, I mean, it happens. Sorry, I should be a little bit, yeah, so this is true. We've derived it. But you can characterize it, the modular flow, with these two properties. So it fixes the structure without actually giving these definitions. Yeah, yes?
Maybe it might help if the formula in the blackboard there, so rho of A to the 1 plus IS, you define it as some f of s.
Yeah.
This formula here is just f of s equal to I.
Yeah.
That's this equality. Here on the right, we have that. So
This.
trace rho A of 201 is equal to.
Yeah.
That's the k-means condition.
Yes, yeah. That's right. Mm-hmm. Yeah. Okay. Yes.
I'm actually confused about something. You naturally derive the two orderings, the two boundaries of your strip. But I don't understand why it was natural to continue past on, trying to make the function periodic.
Well, you're asking why it was natural to do this thing, where I.
Well, the double, which I didn't quite understand.
Let me motivate it by this case. So it's certainly natural to continue here because there's no branch cuts. And the way of saying that is that this correlator is periodic because the operators commute in that case. I'm not sure how natural it is to do that here.
Even then, the periodicity comes from what looks like a special little Loomer space.
Yes.
Is that?
Yeah, I think so. I think that's right. I think maybe, yeah. I like to think of it this way. That's how I like to think of it. Where you take this function and continue it to periodic function in the full strip, in the full complex S plane. And then you can make the statement about the discontinuity across this branch cut. Of course, it's maybe not so natural because this branch cut in general will go straight through. So there's no sense in which I'm, maybe it's not, yeah. It's maybe more natural here because you can continue through. Any other questions? Yes.
Yeah, so when you assume that the state is thermal with respect to the modular Hamiltonian, you show that the correlators are symmetric with respect to the modular flow and also satisfy the KMS condition. So my question is the converse true? Can you start with KMS and symmetry with respect to modular flow and prove that the correlator had to be thermal with respect to the generator of the flow?
Yes, yes. You can do that, yes. Yeah, the question was about the converse, whether starting with modular flow and, sorry, the KMS condition and invariance under the flow for the one-point functions, whether that characterizes, whether that gives you, and the answer is yes. Yeah. Yes. Yeah, so in a thermal theory, yes. I think that's in a relativistic thermal field theory. So relativistic is really important there. However, what should I say? Just in general, if I started with if I just do this in general in quantum field theory, if I had some region and some state, then as I said, modular flow takes a local operator to something that's non-local, and so there's no reason to think that it would commute with another local operator. So.
But if you started with space-like separated operators to begin with, then you would be guaranteed this regardless of the state or the region, right?
At the point S is 0, but I don't really know.
Oh, it's usually just a single point.
Well, yeah. I mean, but in any case, these, yeah. So because as soon as you flow, then there's no reason to believe that it maintains that locality, at least exactly.
Oh, it can instantly become time-like separated, even if it starts out space-like separated?
Mm-hmm, yeah. So this is special to this local flow. Okay. Are there any other questions about this? Okay. Let me do one more case where we know the modular Hamiltonian in CFTs, or in modular flow and so forth, and we know it's local. So I wanted to emphasize, I think I've tried to, but yeah, so there's this distinction between local flows and non-local flows, and that's the language that's used. And it's it's this distinction between whether if I act on an operator with modular flow, whether it stays a local operator or not. So that's the distinction. Okay, so there's another local case, which is the modular Hamiltonian in CFT. If I start with a Rindler space, this is my cut, then you can construct a conformal transformation, or a conformal transformation that leaves invariant the vacuum state, but maps this cut to a ball. It maps this sort of half space here, A, to this A here, which is a ball of some radius. And so if you compose that conformal transformation with, I guess if you act on the density matrix for this region A with this conformal transformation, then you would expect to find the density matrix of this ball-shaped region. And in fact, you can argue that the density matrix is also determined by a modular Hamiltonian, which is local. Now, instead of, you can do that explicitly. You can find this map and you can write it down. So, well, let me first say something about conformal transformations. So this conformal transformation is just some coordinate transformation that leaves the metric invariant up to some overall scale factor omega. And in a CFT, the reason that we don't really care about these overall scaling factors is because the response to changing the metric in a quantum field theory is it couples to the stress tensor, but if I change the metric by something that depends on the metric itself, so this overall scaling, then I just get the trace of the stress tensor here, and so this becomes the trace of the stress tensor. But in a CFT, the trace of the stress tensor is 0, so these become symmetries of the CFT. And then we can find this conformal transformation using this and applying this idea to the flat metric, the Minkowski metric. Okay. So instead of constructing this conformal transformation, what I'm going to do is construct for you the resulting flow. So there was some symmetry, there was some killing vector C that was associated to boosts, right? So this is a boost vector. So flow lines of this vector field look like this. And so instead of just doing this conformal transformation, I'm going to understand the action of this conformal transformation on this vector. Okay, so now we're trying to find this new vector in this space. And the property of this vector is, well, this vector field is that it vanishes. It doesn't have any action at the entangling surface, right? So it leaves fixed this point, right? So these are boosts, but they don't act exactly at the boundary here. So under this conformal transformation, it stands to reason that the resulting vector field will vanish also on the boundary of this region. Okay, so we're looking for C, vanishes here. Okay, so now we're, yes. Yeah, so there's time in these pictures, and I'm not drawing time yet. But so there's a wedge-like region, like the Rindler region, and then what that will map to is the domain of dependence of this ball region, which is this diamond, which is it's a double cone where you start with points here and here, and you take the intersection of those two. But this structure actually just comes out of this idea, and so what we're looking for is some infinitesimal version of this transformation, which is going to construct for us this new vector field, and these correspond to conformal killing vectors. And conformal killing vectors, well, you can just check the condition that the metric is left invariant. Yes. Yeah, so psi in here is d by d eta. Yes, thank you. Yes. So the conformal killing vectors are vectors that satisfy this equation. So this is the conformal, the killing equation, but then we can have some overall conformal or change in the conformal factor delta omega, but then you take a trace of this equation and you get this. So this is some equation for these vectors, and you can solve it in Minkowski space. And in general dimensions, you find the following solutions. So you can have, C. You can have, well, there's various parameters that go into the solutions to this. You can have translations, which are parameterized by A. You can have rotations, which are parameterized by R mu nu. Sorry. Yeah, I really ran up the boundary there. And then you can also have, so these are just the usual killing vectors, so these are just the usual symmetries, but you can also have scalings or dilatations, and then you can also have this special conformal transformation, x mu, which is quadratic in the x's. Okay, so this is the general solution to this, parameterized by various parameters here. So all we have to do now is take this and look for an appropriate vector field that vanishes on a ball. And so there's a unique solution to that. And if you stare at it a while, then this is the solution. So I should pick up to some overall scale, which I've fixed already. I should pick AT. So the T component of this, I should pick AT to be R over T and BT to be minus 1 over 2R, and all of the other things are 0. Okay, and then you write out what this is, and this is this guy. Where I've split my coordinates now into, time and space coordinates. Okay, so we can just check that this vanishes. So this is some vector field in space-time, and you can just easily check that it vanishes on the ball, which is, so the boundary of the ball lives at t is 0, so it's on a t is 0 time slice, and x squared is r squared. The other thing is that the normalization, which I've already fixed here, is fixed by taking, by basically taking this vector field and expanding it really close to the boundary of this region, and then demanding that it goes back to the Rindler vector field. So that fixes the normalization. Okay, so this vector field has a picture. That looks like this. So I'm just going to draw it in 2 dimensions, but this works in any dimensions. So you have, this is the region, this is the ball of radius r. And then you have the domain of dependence of that ball. And the vector field just flows inside this diamond, like this. And of course, as I said, close to the boundaries, it looks like a boost. It also has some action outside of the diamond. And you can just guess. It's the opposite. It goes down here because it goes up here, and so forth. And it also has some action over here that you can work out. Just over there. Oh, goodness. Yes, that's right. So this is a picture of the flow lines of C. Good. And so what are these flow lines? Well, of course, they're the line, they're the lines that you would follow if you undergo modular flow, right? So, okay. So maybe I haven't got to that yet. Okay, but one important thing that you can do now is you can construct the modular Hamiltonian. So we use this same formula that we wrote before, integral over dx t mu nu, dotted into a normal vector, and then dotted into this vector field, c nu. Okay, and so we're going to integrate it over the ball region, which is our region A now. And so just integrating it over this slice, the normal vector is just the time component of this. So just rewriting it, and then taking this component here and setting t to 0, this vanishes, and you just get this form r squared minus little r squared over t2r times the 0, 0 component of the stress tensor. Okay, so, and this is over the A region. Okay, good. So some important comments. So this means that the density matrix is just, is again of some form exponential, some integral over the energy density. So this T00 is just the energy density of the quantum field theory times some effective temperature that depends on R. And so this effective temperature, you can work out this effective temperature depends on where you are. So R is the coordinate from the origin here. So R over, and so notice that, well, it's nice and smooth here, but as you go to the boundaries, the temperature blows up. Okay, so the temperature diverges, and this is exactly the same thing that happens in Rindler space. The temperature diverges as you go towards the horizon. Okay. Yes? Sure. Yeah, I'm using, so this is a vector. This is a vector. Is that what you're asking about? So yeah, yeah. This is this notation where I use derivatives as vectors. And so now I'm still doing that here. Yeah. But here I would have to take the 0 component of this vector, which is this component. Okay, very good. Okay, so the other thing is, which I alluded to, is that if we now do modular flow with this operator, if you start with a local operator, it stays a local operator, but it moves along these lines here. There's an additional subtlety though. So that means, we start with some x here, we apply this, and we get some other operator at some other point. But because this is actually, the generator of this is a conformal killing vector, if this had some scaling dimension, then you also have to account for the fact that there's some rescaling due to the conformal factor. So there's some rescaling here. So this is just a number. So this is still a local operator, but you should be aware of that fact. And this depends on S. Okay, so all right. So the other thing I should say is that there's been many applications of this formula. Various things include, now you can sort of get a handle on relative entropy in CFTs for compact regions. So that's kind of useful to make things compact, so you don't have the infrared divergence of Rindler space. You can use this to bound energy densities. You've already seen some examples of doing that. If you apply it to, so one neat application is that if you apply it to many, it has useful applications in ADS CFT, because there we have this nice formula for the entropy. So then we can use this in combination with the entropy to compute the relative entropy. And there's some relation to Einstein's equations and things like that. Okay, so I think that's all I'm going to say about this. So let me pause for questions. Sorry? Here? Because this is, this is the normal vector. So we're going to integrate along the t is equal to 0 slice. Now it's true, this is a conserved quantity, so I could have chosen to integrate it over any other slice. But of course, it's convenient to integrate it over this slice. And so n is the normal vector, so it's in the time direction. So I get the 0 component here, and this component vanishes when t is 0. So then I only get this component, that component of the vector field. So, any other questions? Yeah.
So when you compute this modular Hamiltonian here, do you have to, when you do that interval, do you have to do any sort of radial ordering of the stress tensor?
So say that again, radial ordering?
Like with the operator ordering? When you interpret it as an operator?
Yeah, well, you have to be a little bit careful because you're in real time, so you have to say where, relative to other operators where it is. If I insert another operator here, then I could do it in various time orderings in real time. But because it's a conserved charge, you can also move it around. So, okay, good. All right, so now I'm going to move on to the next topic.
Wait, can I ask you?
Yes.
Were you going to say more about
Maybe I
the
should have.
branch cuts?
No.
Then I'll ask.
Good.
What kind of branch cuts are they? Like, let's say this simple Rindler case,
They're just power laws.
like fractional power.
Yeah, fractional power. So let's take in this case, it's just the dimension of the operator. Right, which, let's take it to be funny. I mean, you can get logs as well. Yeah.
So in some cases, there's no branch cut if it happens to be an integral dimension?
Yes. Yes. Yeah, usually if it's a free theory, then yeah. Yeah.
Even though the commutator is definitely non-zero, so how can you not have a branch cut?
Well, in some situations in free theories, you can have a commutator being a delta function, right? So,
Oh, I see.
yeah, yeah. Okay. Good. So let's move to the next topic, which is the replica trick. Okay. Okay, so let's, so the goal here is to give some alternative description of, well, to find some way to compute the ultimate goal is to compute the entanglement entropy, but at an intermediate step, we're going to compute the Renyi entropy. So the Renyi entropies depend on, so it's basically you take powers of the reduced density matrix, and you take the trace, and what we'll be able to do, at least in quantum field theory, is do this trace for where n is an integer. But before we get to that, let's just take n to be any parameter, and we can define the Renyi entropies. So n doesn't have to be integer now, as just this. This form is special. Trace rho to the n, when n goes to 1, it's designed so that as n goes to 1, using the fact that the normalization of the density matrix is such that this is 1, when n is 1, that means that log goes to 0, and n minus 1 also goes to 0, so you need the next correction, and so it's easy to show that Sn goes to the von Neumann entropy, or the entanglement entropy, minus trace rho log rho. And so, you can think of this as some intermediate step. So you're trying to calculate this, and then if you can take this limit, you can compute the entanglement entropy. But these are also interesting objects in themselves. So for example, you can think of it's somewhat useful to think of this as some kind of partition function where n. So in particular, if I really rewrite this using the modular Hamiltonian, then this just becomes trace e to the minus n ka. And so what is n? N is like 1 over the temperature. So it's 1 over some effective temperature. And so these are kind of like partition functions. And so now if I knew all of these, in principle, I could do some kind of inverse Laplace transform to extract the spectrum of the density matrix. Right? So they contain a lot of information. But you know, this is just thinking of this as taking some density matrix and raising it to some power. But it turns out that when n is an integer, there's sort of another way to calculate these things. And that's the subject of the replica trick. So maybe let me leave it. So let's just start with a really simple setup, which is just quantum mechanics. So when n is an integer, there's another way to calculate. And actually, it has to be an integer bigger than 1. The idea is that if you had some state in your total Hilbert space, then imagine replicating that state. Okay, so you take that state, and then you replicate your Hilbert space n times, and then you take some state, which is a tensor product of this state, n times in, let's say this is h total tensor to the n. Now, of course, you know, this seems to violate no cloning, but we know this state, right? So let's say we know how to prepare this state, then all I'm telling you is to prepare it n times. Okay, so that's not a big deal. Then in this new Hilbert space, there exists operators. There exists an operator in this thing. So on to the n, such that these powers of the density matrix, trace root of the n, are just some expectation value of some operator, mn, in this replicated state. Okay? So, for example, M2 is sometimes called the swap operator, and it's useful for various reasons. So it's useful if you want to try to compute these things numerically. You know, for say interacting theories where it's very hard, then you can try to do something like computing expectation values of some operator just in this doubled Hilbert space for the second Renyi entropes. It's also useful in that, you know, in some situations you can even try to measure the Renyi entropies because now this is an operator, right? And so, in principle, you can try to measure it in the lab. It has been measured in the lab, yes. Okay, so let me just give the n is 2 case. We'll write it out. So what is this operator? So the swap operator is so firstly, I take some basis of states A and B in the A Hilbert space and the B Hilbert space. So A is 1 to the dimension Hj. Okay, and with this basis, I construct the following operator. Okay, so swap is some sum over A and A prime, A prime. So this is not the identity because I've switched these. And so this is on the first copy. So remember, this is an operator in 2 copies of the Hilbert space. So I'm going to label them by 1 and 2. And then A prime A on the second copy, and then tensored with the identity on the B1, B2 Hilbert space. Okay, so that's kind of simple. Let's give a sort of a pictorial representation for it. So if I have the first replica, which I represent as A1 and B1, and the second replica is A2 and B2, then the swap operator does nothing to B1 and B2, but it swaps A1 and A2. So it does something like this, and then B1 and B2 go straight through. So then what I want to do is, in this sort of tensor network picture of what's going on, I want to feed in the states psi on the two legs. So I have two copies of the state psi. So my picture for pictorial representation for psi is like this, because these lines are representing the A and the B Hilbert space. And so this expectation value, I can just write as well, we have the conjugate states here, these states here. Let me use some colors here. We have this guy, this guy, and then the other things just go straight through. Okay? And so you can take this picture and you can rearrange it. So let me try to do it here. So rearrange it like this. So this is just a simple exercise where the red line is this one, and the purple line is this one, and the white lines are this one and this one. And then this is psi dagger, this is psi dagger, and it's not hard to see that what is this? This is psi dagger, and then tracing over the B part. So this is the B part here, and this represents a tracing. This is the B part here, this represents a tracing. So this just becomes row A, this just becomes row A. I'm taking a product of row A and then tracing. So then this thing, hopefully you can see that, is just trace row A squared. Okay? And so hopefully, so this is for the n is 2 case, but hopefully there's an obvious generalization of this to higher n where I should call it the cyclic swap operator, and then hopefully just by that name you can generalize this. Okay, so this is just in quantum mechanics, and this is useful in quantum mechanics, but in quantum field theory we can give sort of similar pictures. So in quantum field theory, we had our representation for the reduced density matrix from last time as some path integral with some cuts, some path integral with some cuts where we sort of leave arbitrary states on the cuts. So in particular, we did a path integral. So this is the Euclidean time t. And we did a path integral in Euclidean time from -infinity to project onto the ground state. And then we had our cut here. And then we put, some states here, phi A prime, and this represents phi A, rho A, phi A prime. And so now, how do we compute trace rho to the n? Let's take, for argument's sake, take n to n is 3 in this case, and let's just draw a picture of how we would do that. Well, firstly, to compute trace rho cubed, we need 3 representations of this reduced density matrix. So we need 3 copies of this picture. So 1, 2, 3. And then we have cuts here, cuts here, cuts here. So we have phi 1 prime, that's for the first copy. I'm just going to suppress the A label now. this is phi 2 prime, phi 3 prime. And so this would compute phi 1 row A, phi 1 prime, phi 2 row A, phi 2 prime, phi 3 row A, phi 3 prime. And so, you know, that's what this calculates so far. But of course, to compute the traces, all we need to do is identify these two and integrate, identify these two and integrate, and identify these two and integrate. And so what we do in pictures, whenever we identify, so we're identifying phi 1 prime with phi 2, so that's the top part here with the bottom part here. And so what we do in pictures is we sew together these two cuts. So we sew together this with this, top of this, the bottom of this. And then similarly, let me try this one. That. And then the top goes to the bottom here. And then the bottom goes to the top over there. So this one goes like this. Okay, so hopefully that's clear. So there's a cut here, and so the idea is that by sewing this with this cut here, I'm going to get some new manifold where the rule is, if I go basically start cycling around one of these points here, I'm going to go around, I'm going to get teleported over here, I'm going to go around, I'm going to get teleported over here, I'm going to go around, and I'm going to come back to myself. Okay? So we set them set equal, and then integrate, and that just stitches together these cuts here, and so the result is some spacetime, some new manifold, not spacetime, some new space. Where up to some issues at the boundaries of the entangling surface, it's just some some manifold that we can just do a sort of a free path integral on. So there's no boundary conditions, there's no cuts, there's no configurations like that. There's no boundary conditions anymore. So at the end of the day, we get the statement that trace row A to the n is the partition function of the theory. Let's just look at CFTs for now on this new manifold, which I'll call Mn. And so the original manifold was M, which is just R, in this case R to the D. It's a Euclidean space R to the D. And then there's some rules for constructing this manifold Mn. And these rules are given in this picture. Okay, so this is not quite right. This is proportional to. So it's not right because I still need to normalize these density matrices. Whenever you do these path integrals, there's some normalization factors that you're ignoring. So to normalize, I should divide by for each of the row A's, I have to normalize each of the row A's. So I have to divide by the partition function when n is 1, n times. So then the correct formula is, this is the Zm1 to the nth power. And so M1 is the original space without these branch cuts. So this, what is this space? It's some kind of multi-sheeted singular manifold, which has branched over these points, the boundary points of A. So the branch points here and here, here and here, and at that branch point, there's necessarily singularities. Okay, so singularities at the branch points. And what are these singularities? Well, if I look at this picture, and that the circles that I drew there, I'm going around some point in space, and I go around 3 times, or an angle of 3 times 2 pi, and I come back to myself. So what these singularities are conical singularities. They're conical excess singularities. So conical excess is kind of hard to visualize, but so they're conical excess singularities with an excess angle of 2 pi n minus 1. If n is 1, then there is no excess. So if it, so it's easy to visualize if it's a conical deficit. Then this is the picture, or another picture is you just take a sheet of paper and you cut out a triangle, and then you identify these points.
So here, when you write the first line there, you have to fix the relative normalization of n to m1, right?
Yeah, so you...
But if you choose a discrete value of n, how can you find it? How can you fix the normalization?
Well, I think maybe what you're asking is, I have to regularize these in some way. So this is sort of infinite, because you're in infinite...
No, I'm saying like m5, like I can multiply m5 to number 5.
Yes.
I didn't see any problem with that, but I will link to that.
Oh, well, no, I'm trying to get the fact that trace row A is 1, right? So when I wrote this picture for the reduced density matrix, then it's not normalized. Remember, there were all these factors that I threw out when I did the path integral. I projected onto the ground state. There was some factor I threw out there. So at some point, you have to normalize, and this is the normalization step. But yeah, it's true. When you do this, you have to make sure you regulate these 2 things in the same way. Okay, so good. So, right, so yeah, so a conical deficit is easy to visualize, but this is a conical excess, but it's it's the same kind of singularity. One important thing is that the location, so the singular points are at the boundaries of the region. So remember the region, I'm just drawing a picture in 2 dimensions, so the region is just a line here. So this is the region A. And these are at the boundaries. And the singularity lives at the boundary, but there's, where I actually join these manifolds between the 2 different replicas doesn't really matter. So, I had some cut here and I was joining under the cut to the other manifold, but I can actually just deform this, and I could do the joining on a different curve here. So this is really like this is why I'm calling it a branch cut. It's like a branch cut, you can move it around. And the important point are the branch points here. And so, for example, when I move it around, this is now the path integral on some other replica here. What was originally some other replica. So, and I also might be using some jargon here. The replicas are the different copies. Okay, so I have 3 replicas in this picture. Yes?
Why should we find that
because the space is the same if I do this. The space that I get is the same if I identify along a different cut here.
It's the time direction that you are.
It's the Euclidean time direction, yeah. So this resulting space, after I join everything together, is the same if I identify along here or along here. Okay. So that suggests that actually I should think of this just like I did in the quantum mechanics example, where the answer was for trace row to some power was the expectation value of some operator in some state. I should really think of this as Cm n as computing some expectation value of some operator, but now, which is called a twist operator, but really that twist operator lives at the boundary of the region because of this. Right? So I can deform it around, so actually this is where I should think of the operator as living. And this is some equation in in the CFT, but now I need n copies of the CFT. So this is some operator that lives in n copies of the CFT, and there's some technical thing where I can, well, it's convenient to overfold. So I'll explain what that is in a little bit, but this is the equation that you write. So there's some twist operator that lives at the boundary of the region A, and it computes this partition function. So there's two ways to do the replica trick in some sense. There's one way which is, and they're equivalent, and sometimes you use one method and you use them interchangeably. But one way is to just try to calculate this partition function on this complicated manifold, or at least to constrain it or something. And the other way is to think of it as to maybe constrain properties of this operator in this n copies of the CFT. So here there's not n copies, there's just some non-trivial space that the CFT lives on. But here you have to have these n copies. And these n copies live on the original space. So CFT on M1. Yes?
Does the existence of those operators depend on the number of dimensions you're working in?
No. So this picture I'm trying to do in general dimensions. Yeah.
But are the twist operators known in general?
I think you can construct them. Yes. Yeah. So there are techniques. So one important thing is that this operator, just like the entangling surface, is always a codimension 2 operator. So in 2 dimensions, codimension 2 is a point, well, it's actually 2 points, as we'll get to, and so that's a local operator. So we're pretty happy with local operators. In higher dimensions, we now have to use some more non-trivial sort of technology. Yes? Yeah, it should exist for a quantum field theory too. Yeah. Yeah. Mm-hmm. Yeah, it's the definition. Yeah.
So, okay, question. So for the n, it is, say for example, input to Q, it's a swap operator. That is, looks like an operator acting on the whole space of A.
Yeah, so in the quantum mechanics picture, it's a little bit different. It's not exactly the same. I don't really know the best way to say it. Yeah, it's a little.
The swap operator is defined as the swap for all states living on A.
Yeah.
So, but here, if you interpret as the twist operator, that's going to act on the wedge boundary of A. Right? How much do you still like a local operation which represents that sort of non-local operator?
Well, it's not true. It's not true here that you can write it as an operator at the boundary. I mean, that doesn't really make sense.
Yeah.
So this is somehow special to this picture, and actually you have to be a little bit careful about it. So especially when your original space M is topologically non-trivial, so you do have to be a little bit careful. So it's a local operator up to some global issues, but I think there's a better answer to your question. But let me defer it, and I'll think about it. Yeah. Other questions? Yeah. Yeah. So I have some comments about that. Any other questions? Yeah. So I'll explain. I'll say something about that. So if there's some other questions, yeah.
What else does it depend on this twist operator other than the topology of this initiated Riemann surface? It doesn't depend on the conformal invariance because you say that it can be defined on a CFT. It's not on a QFT, not only on a CFT.
So what conformal invariance? What do you mean?
I mean, you can define this twist operator for a QFT.
Yeah.
It means it doesn't depend on the scale invariance of the theory. So other than the topology of this initiated Riemann surface, what are the other entries that you need to fit into construct this twist operator?
Yeah. Some regularization. As always, there's some issue at the point, so you have to do something at that point. And it's the case for twist operators, and you have to regularize. So you can take that as part of your prescription, as that's some more data you need to specify about these twist operators.
So in that case, if you do these 2-point functions, you always you have an ambiguity about some regulator dependence and numbers that you can't fix without knowing the regulators, precise regulators.
Yeah, it's the same as in the entanglement entropy. We had these things. Yeah. Mm-hmm. Yeah, and so I should say that the expansions that I wrote down for the entanglement entropy are sort of are the same or similar for the Renyi entropies, so you can do a similar thing. Okay, so this operator, let me describe it a little bit. I was gonna, yeah, good. So let me just sort of describe it in words, what it is. So this twist operator. So, it lives on this codimensions 2 surface. So let's just draw that surface. And its role in life is that the theory that we're looking at has n copies, and it's defined by what happens when you move around this operator. When you move around 2 pi, you cycle between the 2 different copies, between the n different copies. So you cycle between the copies. So in 2 dimensions, I'll explain this a little bit more in a little bit. But let me make some comments about this. So comments. I don't need this anymore. So yeah, so as someone had asked, this works for the vacuum state, but it also works, for other things. So it works for excited states. It works, and there's been quite a few calculations of this, and so this seems to work quite well. So if I take an operator, one way to make an excited state in the Euclidean path integral is to somewhere in the lower half plane of the path integral, you just insert an operator. So you write that like this. So this is at some imaginary time, negative time. Right, and you need this delta parameter, otherwise this state will not be normalizable, but now you can normalize this state. And so then in your path integral and in your replicas, you just take the same pictures here, but you instead you include an operator psi that lives somewhere here. Say this is, remember this is Euclidean time, and so this would be at minus delta here, and so you insert psi here. But then that was just for the ket, but for the bra you also need the dagger of that operator. So that lives over there. Okay, so you have these 2 operators here, but then you need to replicate this n times if you want to compute trace rho to the n for this excited state psi. Then you need to replicate each of these operator insertions as well, and the result, this might sound a little daunting, is a 2 endpoint function on this non-trivial space Mn. Okay. That's one thing you can do. Another thing you can do is you can look at a thermal state. A thermal state in the Euclidean path integral you just get by, instead of doing a path integral on the plane, you do a path integral on the cylinder. So here's a cylinder. This is still cylinder. This is still the Euclidean time direction, but now you make it periodic, and the periodicity of that is beta, and this would compute, just this would compute trace e to the minus beta h, where h is the normal Hamiltonian. Normal. All right, so this computes this Gibbs ensemble, and so then to compute instead some reduced density matrix for this state rho, appropriately normalized, then you just insert these cuts here. And again, you take n copies, you join them like this, and you just get some other space. So mn now depends on the temperature. Okay. Yeah.
In that case, do the operator insertions become functors?
So in which case, in this, let me talk about two dimensions in a little bit. Okay, so yeah, so yeah. Oh, these things, the size? No, I mean these are just operator insertions. Yeah, yeah. Oh, I see. You're asking. I mean, okay. So then you get some. Yeah. Okay. Yeah. I mean, they're just operator insertions. Yeah. That's all it is. Okay. So that's two comments about what you can do with this. So it's quite powerful. There are other things you can do as well. You don't have to just compute trace row to the n. You can compute other things. You can try to get the relative entropy using these tricks. You can try to get properties of the modular Hamiltonian. It's not just the entropy and the, but yeah, yeah. Sorry? Yeah, so the picture is the same with many intervals. So I'll give an example later. So yeah. Okay, so there's one thing. So the final, so this is all well and good. So we've computed our Renyi entropies for integer n. But then we're really interested in the entanglement entropy. So what do we do? I don't want to keep that picture. So let me get rid of this. So we're really interested in the entanglement entropy. So we need to find some continuation. So so we have the Sn, where n is sort of 2. When it's 1, it's trivial. We have the Sn for these integers up to, say, infinity. And the question is, can we find an analytic continuation, some S of alpha, some continuation, such that S of alpha, when alpha is an integer, is just Sn. So when alpha is some integer bigger than 1. And then if we can do that, we can take the limit as alpha goes to 1, and we can get the entanglement entropy. But of course, this is the trickiest part of the replica trick. And so maybe it's not even well defined. Is it well defined? Well, you might complain that I can take any continuation that you find, and I can add it, I can shift it by some function that looks like this, say, for any function alpha here, and sign vanishes on all the integers, and in particular when alpha goes to 1, this is not vanishing, so it would change the entanglement entropy, right? Usually, usually what you need in this case, or what you're trying to do, is you're trying to find, in particular, you're trying to find an analytic continuation of this, where alpha is now in the complex plane. Usually, you demand that the real part of alpha is bigger than 0. And so you're looking for some analytic function. And to get rid of this possibility, you need some nice behavior at infinity. So if this function is well behaved, it doesn't grow too fast at infinity, then actually there's a theorem which is called Carlson's theorem, which guarantees a unique continuation. And so the growth condition.
It guarantees uniqueness, presumably, not existence.
Okay, possibly.
It probably wouldn't exist.
That, yeah, right, yeah. So I think existence is not really, usually we have a continuation in mind, so I think existence is, we're okay with that. Uniqueness is what we're worried about. And so, yeah, so, and let me just write it here. And the growth condition is that the magnitude of S alpha should be bounded by some some constant times the magnitude of alpha, where C needs to be less than pi. And then there's some uniqueness. Yeah, so this guy. So yeah, if you go back to, yeah, so let me say that in a little bit. But so in particular, that kills this case because, you know, in the imaginary direction, or in some imaginary direction in this, still in this region, a sign blows up exponentially e to the pi alpha. Okay, so that that kills this possibility. And so, you know, okay, so in a finite quantum system, you can check that all of these things are satisfied, and maybe that's not so surprising. So there is, once you know the integer Renyi entropies in a finite quantum system, you can reconstruct the alpha, the analytic continuation, and, you know, yeah. So in quantum field theory, we sort of expect this to be the case, but it's not really, it's, yeah. Yeah, that's right. So we do it with the cutoff, and then we're kind of in a finite quantum system case, and then yes, then we can sort of be happy with this. But yeah. So in particular, there's one issue that I like to point out, but I don't think it's really an issue. After talking to Matt recently, is that there are some situations where we know where there are phase transitions in the Renyi entropies. Right? And so phase transitions exactly correspond to non-analyticities, which would mean this is not an analytic function, so why are we even using this? But you know, you can argue that those phase transitions that we know about have all been found in ADS CFT, and likely they're large N artifacts. Okay. Okay, so are there any questions about this? That's a good question. Yeah, I think it's the same thing, yeah. Yeah, so yeah. Yeah, Van was asking whether this is also true for other things. You don't have to, so one thing you can ask about is, for example, correlation functions like this, and is it the same statement there? Because sometimes you can compute those correlation functions for integer n, and I think it is the same statement. Yeah.
Now in case we have phase transition, this theory will break down because the Sn has a very fast increase.
No, I would say it breaks down because it's no longer an analytic function. Remember, I should think of alpha as is like 1 over a temperature. So it's like a phase, you know, it's like a thermodynamic phase transition. But of course, in finite quantum systems, you can't have those phase transitions. So, well, not for, you can argue that you're not really, you know, in this, say, for example, if you have some compact interval, then the appropriate regularized Hilbert space should be, in some sense, finite dimensional. Yeah, yeah. It bothers me though that we're using the cutoff in this argument. So I'm not, yeah. I'm not sure about this. Let me say that one thing I did want to say is that usually when people have done this, you know, you get some answer, and this answer satisfies many very non-trivial checks. So a very good example of this is the Root-Takinagi formula. So this has been the replica argument by Juan and Aitor gives the Ryutake-Nagy formula, and it should be based on some assumption like this, and the Ryutake-Nagy formula has satisfied an infinite number of checks. Yeah. Yes.
How to think about this more general copying myself from the CFT particle point of view, because it's not clear how the manifold structure would look like the n-sheeted.
When n is not an integer? Yeah, that's exactly the problem, right? So we can't give a description of this. So the idea is that you just have numbers. This computes numbers for each of these integers, and then you have to interpolate. So usually there's some physical thing that you do that sort of makes sense. It makes reasonable sense when you do these continuations. Okay. All right. Okay. So let me talk a little. Yeah. Let me continue. Let me talk a little bit more about CFT methods. Two-dimensional CFT methods. So. Okay, so let's specialize to 2D, 2 dimensions. Okay, so now firstly, the twist operators that I've been talking about, they live at the boundary of the region A, but in 2 dimensions we just have intervals, so the boundary is just 2 points. So usually that's written as twist operators living at those 2 different points. Sigma n xl, sigma n xr, where this is the point xl, and this is the point xr. Okay, and actually, sorry, and then you label this with a minus sign because again, these twist operators are defined where you move around them and you cycle between the different replicas. But what you want is that moving around this guy cycles, k goes to k plus 1 in this direction. But if I go in the same direction for this guy, k goes to k minus 1. Because you go down, you go the opposite direction around the branch cut. So actually, this is some twist operator which has the opposite charge. So this represents some charge, and they have the opposite charge. Okay, so these operators. Live in n copies of the CFT, overfolded by this Zn symmetry. So let's just start with CFT to the n. So if I just have n copies of the CFT, say for example I had some quantum fields, and then my action was just the sum of those quantum fields, so phi k, the different quantum fields, then there's some symmetry that switches me between the different fields. So locally, it takes phi k to phi k plus 1 of x, and k here, k is 0 to n minus 1. And so the part of this, of this overfolding, is just projecting onto states in the resulting quantum field theory that are invariant under this symmetry. So this symmetry is implemented by some unitary operator on the Hilbert space, and let me call it, so this action is g, and g to the n is 1, because if I do this n times, I get 1. So this symmetry is implemented like this, and then you project, and one way to project is to just to sum over powers of this, ug to the k. And so this would project onto Zn invariant states. But when you do this, you get a new thing. So when you do this, when you gauge the symmetry, you get a new thing, which is exactly these twist operators. So, you know, if I just think about a regular point in Euclidean, right? So I have some regular point in Euclidean, and I move around that point, then the different copies of my fields, they just come back to themselves under some, so this is some angular direction theta, and if I take phi k and I shift theta by 2 pi, I just come back to myself. But twist operators, so this, if I put a sigma n here instead, so this is really, there's nothing here. So one way to think about nothing is that it's the unit operator, and instead we're going to insert an operator here and start moving around. And if I move around by 2 pi here, then by definition, the fields switch, so they cycle. So in particular, here I have sort of n copies and they don't talk to each other. But here, as I go around, they talk to each other, and I just get something that has an effective length, which is n times 2 pi. Because of this property, I eventually get back to myself. So this is a twist operator, and it's, you know, it's a local operator, and obviously for these calculations, it's the most important thing to know about this twist operator is its dimension, is its scaling dimension. Okay. So let me very quickly argue what its scaling dimension is. All right, so scaling dimension of sigma n. Well, okay, so in two-dimensional CFTs, it's useful to know very quickly that there's a state operator correspondence. So how this works is that if I have some operator inserted at the origin, then I can just sort of slice open my path integral on circles. I can make some kind of conformal map where this just becomes a picture where these circles, which were labeled by R here, are now labeled by some time on some cylinder. And the different operators on this cylinder correspond to different states in this picture. And so in particular, under this dictionary, you get, you know, so operators map to states, and vice versa. The twist operator that we've been discussing maps to something called the twisted sectors. Which has this property that you have the n copies joined like this. And in particular, scaling dimensions of these operators map to energies on this cylinder. So if you compute the energy of this state, then it maps to the, up to some constant shift, maps to the scaling dimension of that operator. So there's some relation, which is that the energy of this operator is 2 pi divided by L, where, sorry, maybe I should, yeah, divided by L, where L is the size of this circle times the dimension of the operator up to some shift. So in particular, an important part of this, well, it's related to the shift, is that if I think about the CFT on a cylinder, there's always a negative Casimir energy that just comes from the fact that you're living on a compact manifold, which is S1. So it's a Casimir energy density. So Casimir energy density, which is fixed in terms of rho of x. So local density is fixed in terms of the central charge of the CFT. C is the central charge. It's also the same thing that appears in the Weil anomaly. So this is some universal formula. You can derive it. I'm not going to derive it. But it allows us to compute the dimension of these twist operators, because now you see that, well, this means the energy of the vacuum, which is this picture here. So if I take this unit operator and I map it to a state on the cylinder, then it maps to the vacuum. Then the energy of that vacuum due to this Casimir effect is just minus C, this energy density, times the length of the circle, which is L, times a factor of n, because there are n, there's n copies of the CFT. So that's the energy of the vacuum, and the energy of the twisted sectors. Well, because I have this wrapping around here, the effective length of the cylinder now is n times that length. So the Casimir energy is actually less, right? Because of the Casimir energy density depends on the size of the circle, and now I have a bigger circle, so I get a factor of 1 over n squared from this. So it's minus C over pi 6nl squared, and then nl, because that's the effective length. So the effective length in this case is nl, but now I only have 1 copy of the CFT. Okay, so then just to remove this shift here, I can just compute now the dimension of the twisted operators just by using this formula and taking the difference of these two things. So let me write the energy. The difference in the energies, the vacuum, is then just C pi over L, n minus 1 over n. And so that implies, assuming the dimension of the unit operator is 0, the dimension of these twisted operators is just C over 12, n minus 1 over n. So that's the final formula, and I'm out of time, so next time we'll use this to calculate the Renyi entropies. Okay, so we finish there.